Single mean. In this section, we'll see how to test the null hypothesis that the population mean is equal to some hypothesized value. First, let's look at an example. Suppose an experimenter wanted to know if people are influenced by a subliminal message. She shows 9 subjects a series of 100 pairs of pictures, like the ones shown here. As each pair of pictures is shown, a subliminal message is presented suggesting the picture that the subject should choose. The null hypothesis is that the subliminal message has no effect on which picture is chosen. More specifically, the null hypothesis is that the mean number of the times suggested picture is chosen in the population is 50. That is, if there were no effect on the subliminal message, then subjects would choose the picture with the message 50% of the time. Since we are testing 100 pairs of pictures, 50% of the time is equal to 50 pairs. Written formally, the null hypothesis is that the population mean, or mu, is 50. This table shows the frequency that the suggested picture was chosen by each of the 9 subjects. You can see that the sample mean is 51, which is greater than the hypothesized population mean of 50 by 1. To test the significance of the difference from the null hypothesis, we assume that the null hypothesis is true, and then we calculate the probability that a sample mean would be greater than the population mean by 1 or more. If this population probability is low, then doubt is cast on the validity of the null hypothesis. The first step is to determine the sampling distribution of the mean. As shown in an earlier section, the mean of the sampling distribution of the mean is equal to the population mean, which is, in this example, 50. The standard deviation of the sampling distribution of the mean, also known as the standard error of the mean, is equal to the population standard deviation divided by the square root of n. In practice, we rarely know the population standard deviation, and therefore use the sample standard deviation as an estimate. However, it is useful to see how the probability is computed when the population standard deviation is known, since this will help you understand how it is calculated when the standard deviation is estimated. The subliminal perception example is one of the exceptional situations in which the standard deviation is known. Specifically, if the null hypothesis is true, then the population standard deviation is 5. This value was calculated from the binomial distribution for an n equal to 100 and a population proportion pi equal to 0.5. The formula for the standard deviation is shown here. It is not critical for present purposes that you recall this detail of the binomial distribution. It is important to know that this is an example in which the population standard deviation is known to be 5. Next, we determine the standard error. Substituting the standard deviation of 5 and n of 9 into the equation, the standard error is calculated to be 1.667. Be careful not to confuse the n of 100 shown previously, which represents the number of pairs of pictures each subject saw, with the n of 9 shown here, which represents the number of the subjects. To recap, we want to know the probability of obtaining a sample mean of 51 or more when the sampling distribution of the mean has a mean of 50 and a standard deviation of 1.667. To do this, we need to assume that the sampling distribution of the mean is normally distributed. We can use the normal distribution calculated to find the probability. Type in the mean of 50 and the standard deviation of 1.667. The calculator then works out the area under the curve above 51. The probability of obtaining a sample mean of 51 or larger is 0.274 and is displayed here as the shaded area under the curve. What can we conclude from this? The probability is 0.274 that a sample mean of 51 or higher would be found even if the subliminal message has no effect. This is a relatively high probability. The probability should be much lower, such as less than 0.05, in order to strongly support a conclusion that the independent variable has an effect. The probability of 0.274 indicates that the finding might well have been due to chance, and therefore we do not reject the null hypothesis. In short, this experiment does not provide convincing evidence that subliminal messages have an effect, nor does it demonstrate the subliminal message has no effect. We just performed what is called a one-tailed test because we computed the probability of a sample mean being one or more points higher than the hypothesized mean of 50. That is, we tested in one direction only. We only looked at the area under the distribution above 51. To test the two-tailed hypothesis, compute the probability of a sample mean differing by one or more in either direction from the hypothesized mean of 50. To do this, work out of the probability of a mean being less than or equal to 49 or greater than or equal to 51. So when we're talking about tails, remember that we mean the end of the distribution. Again, we can use the normal distribution calculator to work out the two-tailed probability. As you can see, the probability is 0.548, which, as you might have guessed, is twice the probability of 0.274 shown earlier. Before statisticians could get hold of these fantastic calculators, they had to find probabilities the old-fashioned way. They did probability calculations using z-scores and the standard normal distribution. To do this, compute z using the formula shown here. Z is a value of a standardized normal distribution. M is the sample mean, mu is the hypothesized value of the mean, and sigma sub m is the standard error of the mean. For this example, z is equal to 51 minus 50 divided by 1.667, which equals to be 0.6. We can find the answer using the normal calculator with a mean of 0 and a standard deviation of 1, which are properties of standard normal distribution. Notice that the probability shown here as the shaded blue area is the same as when we calculated it earlier for the one-tailed test. Of course, in the old days, statisticians would use a table, not a calculator. Unfortunately, in the real world, it is very rare that we would know the mean and the standard deviation of the population. Typically, we have to estimate using our sample data. We estimate the population mean with our sample mean, estimate the population standard deviation with the sample standard deviation, and estimate the standard error of the mean with the estimated standard error of the mean. To take a real-world example, we'll use the data from the ADHD treatment case study. We'll summarize the study here, but for the more details, refer to the case studies section. These data consist of the scores of 24 children with ADHD on a delay of gratification task. Each child was tested under 4 different drug dosage levels, so we're looking at a repeated measure of design. But we'll simplify a little and concentrate on 2 conditions instead of all 4. Here you can see the results of 4 children in the placebo condition, D0, who received 0 milligrams of the drug, and in the high dosage condition, D60, which is in which they received 6 milligrams of the drug per kilogram of body weight. Notice that difference scores are shown here in the last column. When children perform better in high dosage condition than in the placebo condition, the difference scores is positive, and when children perform better in the placebo condition than in the high dosage conditions, the difference score is negative. If the drug has a positive effect and improves performance on the delay of gratification task, then the mean difference score in the population will be positive. If the drug has no effect, then the mean difference score in the population is 0. This is the null hypothesis. To test the null hypothesis, we do a t-test. To compute t, we take a statistic, subtract the hypothesized value, and divide that by the estimated standard error of the statistic. Because we're testing a single mean, we take the sample means minus the hypothesized value of the population mean, and divide it by the estimated standard error of the mean. You might notice how similar this formula for t is to the formula for z that we saw earlier. Getting back to our ADHD example, we still need to calculate the estimated standard error of the mean to complete our formula. The estimated standard error of the mean is computed by dividing the standard deviation by the square root of n. It equals 1.54. N is 24 because there were 24 subjects, even though the data from only the first 4 were shown previously. Now we can compute t. The mean of the 24 difference scores is 4.96. We subtract the hypothesized population of the mean of 0, then divide by the estimated standard error of the mean, which we've just worked out to be 1.54. This gives us a t-value of 3.22. To get the probability value of a t of 3.22, we need to know how many degrees of freedom we have. The degrees of freedom is equal to n minus 1, which is 23 in this case. Notice that n is the number of differences scores because there are the scores we are analyzing. Now that we know the degrees of freedom and the t-value, we can consult the t-distribution calculator or a t-table in a statistics textbook. As shown here in our two-tailed test, the probability of getting a t-value of less than negative 3.22 or greater than 3.22 is only 0.0038. This means that if the null hypothesis that the drug has no effect were true, then the probability of finding a difference between means in the placebo and drug conditions as large or larger in either direction as the difference found in the experiment is 0.0038, which is very low. Therefore, the null hypothesis that the population mean difference score is 0 can be rejected. We are justified in drawing a confident conclusion that the population mean for the drug condition is higher than the population mean for the placebo condition. Finally, let's review the assumptions of a single mean t-test. Firstly, we assume each value is sampled independently from each other value. And second, we assume the values are sampled from a normal distribution. In this example, the values are the difference scores.